Hello, knowledge seekers! Welcome to Remedial Tutorial Academy. In this video, I just want to show you how to write a complex number in polar form. So normally you're used to seeing them in the form that looks something like this, a plus bi. Let's pick an actual number here. Let's say that we have the complex number that is 2 plus 3i. So if we go ahead with their standard geometric interpretation of this, we can plot this complex number on the complex plane, where a is 2 and b is 3. So we can think of the complex number set as a point in this Cartesian space, just with the coordinates a, b. But there's another way that we can represent this, and it is with polar coordinates, which we would have an angle here, theta, and the lengths here, r. We can basically identify any point with either Cartesian or polar coordinates. Alright, so the first thing that we can do here is we can figure out really easily what r is, because r is just equal to the modulus of z, which was equal to the square root of a squared plus b squared. And again, if you look at this geometrically, or thinking about this as a triangle, it's basically a Pythagorean theorem, where a squared plus b squared equals c squared. So if we just fill this in a little bit, we get the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9, which is the square root of 13. So this is the modulus of z, and this is also our value for r when we're looking at it in polar form. And theta is pretty easy to get as well, because the tan of theta is just equal to b over a, right? It's the opposite over the adjacent side. And we can just rearrange this and say that the tan inverse of b over a is going to give us theta. And if you remember, when we're dealing with polar coordinates, we should be using radians. The theta we call the argument of z. Sometimes you'll be hearing that. And if theta is between negative pi to positive pi, we call it the principal argument. And the reason we make this distinction here for the principal argument is because there's actually an infinite number of thetas that work for defining this complex number in polar form. Because we have, if we imagine that we start rotating our angle here from the real axis, we can come out to theta. But if we add another full rotation, which is 2 pi radians, we're going to have a different theta. It'll be basically to this theta, this angle, plus 2 pi. And then that satisfies our format here. We can add another 2 pi, we can add another 2 pi, we can subtract basically any integer multiplier of 2 pi's. And so they're basically the simplest theta that we can deal with is one that is basically in this first half of the rotation, or in this area. So if you're using your calculator like this with the tan inverse function, it will spit out a value. And you just have to check by basically, I would recommend plotting the vector here as you can using a and b in the Cartesian point and just identifying which quadrant this is in, 1, 2, 3, or 4. And I would just double check that the value that you're getting for your theta here actually reflects that if you're in the right quadrant, not the one that's like diagonally across from it. Because that is possible using your calculator. If that does happen, then you just have to subtract pi from it to get the proper theta that we're looking for. Okay, so now what we want to do is we want to actually just write the complex number in polar form. So if we start with the form z is equal to a plus bi, we can convert this from a's and b's to r's and thetas. So if we look down here, a is equal to r cos theta, and b is equal to r sine theta. So we can make this substitution here. So we have this is equal to a, so a is our cos theta, and plus bi, so b is our sine theta times I. And it's actually nicer to write the I out front, r sine theta. What we can do is we can pull out the r because it's common to both terms, so we have r times cos theta plus I sine theta. And now we have it all in terms of r's and thetas. And sometimes you might also see it written like this, where we have the modulus times cos theta plus I sine theta. But whether or not we use r or modulus, basically when we have modulus times cos theta plus I sine theta, or r times cos theta plus I sine theta, now we have converted it into polar form. So let's actually write what we have here for our numbers. We need to figure out what theta was. And so theta is equal, and we can continue over here, theta is equal to tan inverse of b over a. So the tan inverse of b over a. So b is 3 over 2. If we put this in the calculator with radians on, we find this is 0.983. And the decimals go on forever, but let's just cap it at 3 here for now. So this is equal to theta. We have theta, we also had r right here, so we can write our complex number here. We have z is equal to r, which is root 13, times cos of 0.983 plus I sine of 0.983. So there we go. That is the complex number z written in polar form. And just to remind you guys, that is the same thing as it being equal to 2 plus 3i when it's written in the more familiar form that we're used to. Thank you so much for watching. I hope you enjoyed. Please comment down below what are the topics you'd like for me to review. I upload new videos every day. Don't forget to subscribe and share for your friends and classmates. See you next time.